Welcome to the deep dive. Today we're heading high into the Himalayas, looking at a really huge infrastructure project, the Rishikesh-Karnaprayag railway line. If you're someone who likes to get the gist of these big developments, understand why they matter, but maybe without wading through all the super technical stuff, then you're in the right place.
Definitely. And we've got a great source to help us understand it all, an interview with Pradeep Goer. He's the chair and MD of Vikas Nigam Limited, RVNL. They're the ones actually, implementing this whole massive project.
Right, so our mission today for this deep dive is to really get under the skin of the key challenges and also the, frankly, inventive solutions they're using to build this railway. We'll focus a lot on the tunneling, which sounds incredible in that environment, and also touch on the strategic side of things. Okay, so let's start there. Why is this line so important?
Well, fundamentally, it's about connectivity. This line is going to create a reliable link, an all-weather link, to these pretty remote hill communities. You know how vulnerable the roads up there are. Landslides cut them off all the time.
Yeah, constantly hearing about that.
So this railway, it offers a much safer, much more dependable way for people to travel.
That's huge for the locals, obviously.
Oh.
But there's a strategic angle, too, isn't there?
Oh, absolutely. It carries significant strategic importance. It's part of a bigger picture regarding the China border. And importantly, the tunnels themselves are designed so that heavy military gear can be moved discreetly, under camouflage, basically.
Wow, okay. Moving heavy equipment secretly through tunnels, that really highlights the strategic thinking. And I heard the plans don't just stop at Karnaprayag.
That's right. The longer-term idea is to extend the line. Think Joshimath, Gangotri, Yamunotri, huge for the Charbon pilgrimage. And there's also strong interest, particularly from the army, in pushing it even further to Mana. That's near the China border, way up high, around 3,500 meters.
3,500 meters, that's serious altitude.
Mm-hmm.
What's the status on those extensions? Are they happening?
Well, RVNL has done the homework. They've completed the detailed surveys, worked out the costs, and sent that to the railway board. But the final green light hasn't been given yet. The Army's push for the Mana Link, though, really underlines how important they see it strategically.
Got it. So, importance established. Now, the engineering.
Mm-hmm.
Tunneling through the Himalayas. T8 tunnel you mentioned. What's the story there?
Right, T8. It's going to be the longest railway tunnel in India once it's done. And a major challenge right from the outset was finding places to actually start digging into the mountain along its route. Very few openings.
Limited access points.
Yeah.
Okay, so traditional digging methods would be slow.
Extremely slow. With conventional excavation, the estimate was something like 9 years, just for that one tunnel.
9 years, okay.
So that's why they made the call to bring in a tunnel boring machine, a TBM.
The TBM in the Himalayas. I thought that was considered, well, risky given the geology.
It is. It was a bold decision. People are generally quite cautious about using TBMs there because the geology is just so complex, unpredictable. You might think of the Alps maybe, but the Himalayas have that active tectonic plate movement. It adds a whole other layer of difficulty. The mountains are literally squeezing.
So what kind of rock are we talking about? Is it like granite, really hard stuff?
Not really, no. The average strength where T8 is going through is about 35 megapascals MPa. Now, to put that in perspective, granite is often over 200 MPa, so 35 is, well, it's relatively weak.
Okay, much softer rock.
Yeah, which means it's fragile. There's a real risk of the rock squeezing inwards, the tunnel shrinking, or even collapsing as they excavate.
Right, sounds incredibly challenging.
Yeah.
So how did they approach figuring all this out? How do you tackle that?
They started with really intensive investigation. RVNL used something called airborne electromagnetic testing. Basically, a helicopter flies over with this special frame, sending signals down into the mountain to map out the rock layers, the strata, deep inside, like a high-tech scan.
Ah, okay. Getting a picture of what's inside before you start digging. Clever.
Yeah.
And the actual excavation.
Top-of-the-line machinery. We're talking advanced jumbo drills, loaders, shotcrete machines that spray concrete for immediate support, multi-service vehicles, the works. Even the standard drill and blast technique was refined. Much more precise blasting to avoid damaging the surrounding rock more than necessary. Overbreaking, they call it.
And I heard RVNL did something interesting with the risk, with the contracts.
Yes, that was quite key, actually. They decided RVNL would take on the geological risk. They basically told the contractors, look, if you hit unexpected bad rock or major problems, we'll compensate you. That gave contractors confidence and really helped streamline the whole tendering process. Shared risk,
That's smart. Take some pressure off the contractors.
Yeah.
Now, shifting slightly, the interview mentioned some critical decisions about the route itself, the alignment. What was the logic there?
Yeah, this goes back to that idea of sharpening the axe before you start chopping. RVNL spent about 6 years just on surveys and investigations before major construction started. The thinking was a really well-planned route avoids a ton of problems later on.
Makes total sense. Measure twice, cut once on a massive scale. Did they learn from other big projects?
Absolutely. The Kashmir Rail Link project was a big teacher. A key lesson was about approach roads. In Kashmir, they had to build something like 215 kilometers of roads just to get equipment and people to the construction sites. It was huge.
15 kilometers of extra road.
Yeah. So for this line, they were really strategic. They located the tunnel portals, the entrances, close to existing highways wherever possible. The result? Only about 11 or 12 kilometers of new approach roads needed. Massive difference.
Huge saving in cost, time, effort. What else influenced the route?
They also tried hard to avoid needing massive, super expensive bridges. You know, the Srinagar line has those iconic huge bridges like Chenab, beautiful but complex and costly. Here, they chose an alignment where the highest bridge needed is only around 50 meters.
So avoiding the mega bridges.
Exactly. Saved money, time, resources. Just a more optimized approach based on careful planning.
It really sounds like they thought through every angle.
Okay.
Let's talk about the gear. That TBM especially. Where did it come from? How do you even get something like that up into the mountains?
Right, the machinery. Lots of it came from Europe. Drilling stuff from Epiroc in Sweden, Sandvik in Finland. And the TBM itself, that massive machine, was from Herrennecht in Germany.
Germany to the Himalayas. I'm picturing the journey. Must have been a nightmare.
Oh, it was a huge logistical challenge. Had to be dismantled in Germany, shipped all the way to Mundrapur in India, then hauled overland, including through those winding mountain roads past Rishikesh. There was this one bridge over the Ganga, about 100 meters long. They weren't sure it could take the weight.
Seriously, what did they do?
They had to do full-on load testing on the bridge before they dared move the heaviest parts across.
And the heaviest part was? How heavy?
168 tons in one piece.
Whoa. 168 tons. Why not break it down more? Seems like that would be easier to transport.
That's a really good question. They could have broken it down further, but they specifically chose to transport that main 168-ton section as a single unit. The reason was to protect the critical components, the main drive, the shields. These need precise factory finishing, trying to reassemble or repair them perfectly inside a dusty tunnel. Almost impossible.
Ah, okay. Maintaining that factory precision. And I guess assembling lots of small bits on site risks dust getting into delicate parts too.
Exactly right. Dust is a major enemy for those complex seals and bearings. This machine cost around 250 crore rupees, about 6.8 meters in diameter. Needed super careful handling. They actually had to lift it vertically, turn it, then lower it horizontally again just to maneuver it through some tight spots in the way.
Incredible. And assembling it on site.
Took about 2.5 months just to put it together at the tunnel entrance.
2.5 months. Okay,
Yeah.
So given that huge lead time, ordering it, shipping it, assembling it, they must have started digging from the other end too, right? They wouldn't just wait.
Correct. That whole process from ordering the TBM to it actually starting to bore took about 16 months. So yeah, they absolutely started work from the other end of that T8 tunnel, the 14.57 kilometer one. They used a different method there, the new Austrian tunneling method, or NETM.
NETM.
Right.
So digging from both ends to meet in the middle, how did the progress compare? TBM versus NETM.
The TBM was definitely faster once it got going. It chewed through 10.47 kilometers in about 760 days. That averages out to roughly 415 meters a month. The NETM section started earlier from the other side, covered the remaining 4.11 kilometer.
415 meters a month with the TBM. That sounds really fast, especially given you said the rock wasn't ideal.
It is incredibly fast for those conditions. Mr. Gaur actually mentioned it's the second fastest rate achieved globally for a TBM in that size category, like 9-10 meter diameter tunnels.
Second fastest in the world. What was faster?
A tunnel in Spain, the Cabrera Tunnel. But, and this is key, that was through much easier geology. Limestone, much more stable.
Ah, okay.
Tunneling through the kind of phyllite rock they have in the Himalayas is much tougher. Stronger rock is actually easier for TBMs in some ways, so hitting that speed here, yeah, it's a serious achievement.
Really puts it in context.
Right.
Okay, so phenomenal progress. What's the finish line look like? When might trains actually run?
The target for starting train operations is currently December 2026. And the overall tunneling progress across the entire project is amazing. There's about 213 kilometers of tunneling in total, counting main tunnels and escape tunnels. They've already done 195 kilometers
Wow.
in just 3 years and 9 months. The aim is to get all the excavation, the digging part, finished by the end of this year, 2025.
That is seriously fast work, quite the pace. After this huge project wraps up, what's next on the horizon for RVNL?
Their next big focus is another significant line, the 63-kilometer Banapali to Bilaspur line that connects Punjab and Himachal Pradesh. And there are already thoughts about extending that one eventually too, potentially all the way up to Leh and Ladakh. Huge implications for connectivity there as well.
Right, okay, so let's just sort of pull this together. It's been a fascinating deep dive. We've seen the strategic importance of this Rishikesh-Karnaprayag line for locals, for pilgrimage, and critically for national security near the border. We've dug into the massive engineering hurdles, especially tunneling through that tricky, fragile Himalayan rock. And we've looked at the smart solutions, the high-tech investigation, the cutting-edge machines like the TBM, and that clever risk-sharing approach with contractors.
And it's really worth stressing again how much that early planning paid off. Learning from Kashmir, positioning tunnels near highways, avoiding those giant bridges, that upfront investment in investigation and alignment saves so much hassle down the line.
Absolutely. It's a real case study in how foresight, technology, and learning from the past can tackle these giant infrastructure projects. And it kind of leaves you wondering, doesn't it, when you see the scale and complexity here? What other challenges that seem impossible today might be tackled tomorrow with this kind of thinking? Maybe something for you, our listener, to think about that constant push and pull between our big strategic goals and the sheer engineering realities of working with the natural world. Thanks for joining us for this deep dive.